We acknowledge the first Australians as the traditional custodians of the continent, whose culture is the oldest living culture in human history. We pay our respects to elders, past, present and emerging, and we respect their cultural heritage, beliefs and relationship with the land. We extend our respect to all Aboriginal and Torres Strait Islander people here today. They share the memories, traditions and hopes of the traditional ancestors with the new generations today and in the future. We would also like to thank them for looking after this land for thousands of years.
Good morning, everyone, and welcome back to our second session for Earth Science Week. My name's Karen from Virtual Excursions Australia, and we're very excited to be able to support this program, proudly sponsored by Geoscience Australia. And we have the amazing team from Geoscience Australia joining us today for our Innovations in Earthquake Science session. So if you have questions for the presenter, please put them in the Q&A. And if you are asked a question by the presenter, please put that information into the chat. You will be sent a copy of this recording as well if any of your students haven't been able to join us today. So I'm going to pass you straight over to Tamara from Geoscience Australia for this fabulous session for Earth Science Week.
Hello, everyone. So as already said, happy Earth Science Week. So we are going to be doing a lot of fun things today. As Karen already said, my name is Tamara and I'm from Geoscience Australia and I'm part of that education team. And we're going to basically take today to learn a bit about earthquake science and a lot of the innovations around it. So just before we dive in, I'd also like to acknowledge that I'm joining you from the lands of the Ngunnawal and Ngambri people here in Canberra, where science has been done in all country across Australia for thousands of years and continues to this day. So let's dive into that science. So today, we're going to be learning a bit about what an earthquake is, how we monitor for earthquake hazards, a little bit about the impacts of an earthquake after or during its occurrence, and also those innovations. The reason we're focusing on innovation today is that the actual theme for this year's Earth Science Week is around geoscience innovating for Earth and people. So really want to highlight all the different things that have happened over the years to make this practice of monitoring for earthquake hazards a lot more cleverer and more efficient. As we're going through, as Karen already said, there will be a couple questions that I'm going to ask you, so pop those answers directly into the chat. And for any of the questions you have that you want to ask me, by the end of the presentation, I'll be able to answer all of those. So pop any of those burning questions in the Q&A. So let's dive on in. So we're probably aware that there's lots of different types of natural hazards that we experience in Australia. And these are just a few pictures of some of those common ones, like bushfires or severe storms or flooding. And earthquakes is probably one that you may not be as familiar with depending on which part of Australia you're tuning in from. So we're going to focus on that today because though we don't have as many earthquakes in Australia as some of our neighbouring countries, it's still a really important hazard for us to be prepared for and understand as a whole of Australia. So to dive on in, your very first question is I want you to think about what is an earthquake? How would you describe an earthquake to someone? So you can either think, pair, share with the person next to you, or you can pop your answers in the chat. And I'm going to give you 30 seconds starting now. I can already see a few answers coming through. Keep them up. So got a few more seconds. Alrighty, team. Still keep giving those answers in the chat. So there's already a few different ones I've seen so far, but we've got kind of a simplified explanation of how we like to describe earthquakes. So let's bring that up now. So in basic terms, if you had anything to do with shaking or vibrations, you're pretty much right on the right track. So basically earthquakes are shaking in the ground caused when rocks are under stress or pressure. So there's lots of different things that can cause that stress and pressure, but it's just about that energy being released, and then we see that in the form of shaking. And so the important thing when you see this maybe in the news or in other locations is that we describe the amount of energy by its magnitude. And so magnitude is just a number to represent how much energy or how big does that earthquake seem. It can start from really low numbers up to the largest earthquake we have in recorded history was a magnitude 9.5. And that was located in Chile in South America in 1960. So a really big earthquake. But there's lots of earthquakes all in between that range that can be just a little bit of shaking up to a bit more of a destructive earthquake. So we'll find out a bit more about that today. And one of the big things that we do here at Geoscience Australia, where I work, is that we actually monitor for these earthquakes in our country, but also keep an eye on our neighboring countries and other parts of the world as well. And the way they're able to do that is in Australia, we have 150 different seismic stations set up, and it looks something just like this. They're often in remote locations or at least a bit further away from main city hubs. And that's often because we're trying to detect the natural vibrations in the earth, like earthquakes. And if it's too close to a city, you might pick up a bit too much of the human vibrations, like cars driving on the road or construction, or if people were walking right on top or near the sensor. So often they're going to look like these sort of huts out in a remote area. We have our solar panels to make sure we can power that station. We have the satellite dish to send all of that important data back to us here in Canberra. And inside that hut, we can sort of see a bit more technology in there. Mostly it's a couple extra computers and devices to help gather or interpret that information. And the most important thing is actually in the ground inside that hut. There's a borehole that will go down into the ground. So then you've got the little green and yellowy sort of device sitting at the bottom of that, touching the rocks. And that is our earthquake sensor or seismometer, the thing that will actually detect the earthquakes. And there's lots of different types that we can see of these things, but I have one with me here today. So I'm going to show you our version of our seismometer. So it doesn't look very interesting from the beginning, but when we pull it off, we can see there's quite a lot of different parts to this. So we can see there's some clever circuitry at the top. We've got our main cable, which normally connects up to either the computers or directly to the satellite. And the most important thing is this little bit here, which is like a little metal weight. So you can see I can kind of wiggle and move it up and down. And what happens is that when this is placed in the ground, when the ground begins to shake, the whole thing will begin to shake with it. And every time this happens, that little weight will change where it's sitting. And this means that we can detect that the whole device is moving. And every time it moves, it sends a signal down the cord, which can be sent across to us to interpret that data coming in. So this is kind of an older model where it can only go up and down, but modern day versions of seismometers can actually detect in all directions, which is really cool. And so once we've collected that data, we've got to actually see what's happening to be able to interpret it. So what will happen is it will come to something like this in the more older technology. So this is a seismograph that will visually show that data that's coming in. And this can be this version. So this is a metal drum with some paper on it. And basically it's drawing a line with a couple little minute notches you might be able to see on the screen. And that just represents nothing's happening. It's just recording. There's no shaking that the sensor has detected. And when an earthquake happens, you'll see a really clear squiggle pattern start to be drawn on the page. And this is how it used to always be to monitor earthquakes. And you would often have to have the seismometer directly connected to one seismograph out in those remote locations. So trying to gather all that information together was much harder because you would have to go to each station to have a look at it. So now we have advances with our digital technology, so we can have multiple sensors send it through to one screen. So this image here is actually from our National Earthquake Alert Center. So that's the place where we can monitor all these earthquakes, and that's in the same building I'm in right now. And we can see our two seismologists or scientists who study earthquakes are keeping an eye on all the different recordings coming through. Now, it's a little hard to see those lines, so let's bring that in a little closer. So what we can see here is that every single time there is one horizontal line, that represents one sensor somewhere in the world. And that could be in Australia, but we also receive information from sensors from other countries. It's like a shared global network. And one of the best things about innovations in technology is that being able to see all of these sensors in one location means we can better monitor for earthquakes in a broader scale and especially in a global scale, which is quite challenging without this. So that's been a massive improvement towards earthquake innovations. And the important thing too is not only are we monitoring for these earthquakes, but when those earthquakes are detected, we are holding on to and collecting that data. So there becomes a historic record of all the earthquakes that are coming through. And that's really important for the next step. It's important to know when earthquakes are happening so you can respond to them. But if using that data, we can start to create 3D maps and models to better understand why it's happening, where it's happening, and who's at risk. So I'm actually going to show you one of these 3D models that was created by one of the scientists here at Geoscience Australia. And this is going to show all the earthquake locations for historic earthquakes across the entire globe. So let's flick across now and have a look at that. So we can see that we've got Australia as the focus at the moment, and I'm just going to zoom out a little bit further. So it looks like a lot is going on this page, but basically we've got our 3D globe that we can move around, and all of the dark blue dots represent earthquakes. They're the ones closest to the surface, and we can see in some locations we've got this kind of rainbow effect. And what this represents is earthquakes going deeper into the earth. All the way down to red is quite deep into the earth. And I'm just going to take a moment and rotate around the earth and let you make some observations. What do you see when we're looking for earthquakes? So I'll give you a moment. You can pop your observations in the chat or just talk to the people around you. So we're passing in between Africa and South America now. And we're going across the entire of the Pacific Ocean and heading back towards Australia. So I can see there's already a few observations coming through. So a few spotting certain countries they recognize. That's very good. Geography knowledge in there as well. And I guess my main question is, when we look at earthquakes, do they look like they are evenly spread across the whole world? Or does it look like they're kind of clustered in certain areas? Someone said it looks like Australia isn't having any earthquakes. Yeah, we'll come back to that. It's a bit tricky to see on this model because it's half transparent, so I can see through the earth as well. So it makes it a little hard to see this sometimes. Yeah, this is definitely clustered in certain areas. So we can see that we've got a big cluster here around Indonesia, through Papua New Guinea. It goes all the way down through to New Zealand. But if we go into the middle of the Pacific Ocean, there's actually pretty much very little earthquakes across there till we hit the next edge. So what's happening here is that this is based off a thing called plate tectonics, which you may or may not have heard of before. Basically, what that means is that the Earth is made of lots of different layers, And the outermost layer, the layer we live on, is called the crust. And the crust is broken up into lots of small pieces. And those pieces will move around and interact with each other. They'll move in different directions and different speeds. And because they're moving in those different directions and speeds, they'll often interact with each other at their edges. So this means that the plates might collide together as a convergent edge. They might pull apart, so divergent, or they may even slide past each other, and that's transform. And so, depending on what's happening, each of those situations can trigger some earthquakes to occur. But that explains why at the edges of plates is where we're going to see a higher concentration of earthquakes, either a really big cluster, like we can see in Indonesia, or even this small sort of line of earthquakes that we can see around below Africa and in between Africa and South America, all following up here through that water bit. And so this means that most of our earthquakes in the world will be clustered at those edges. However, we had a comment about Australia, and it's really hard to see in Australia. So we're going to try zooming in and having a bit more of a look. But we also can do something really special with this model. We can adjust the opacity, so how clear it is or in terms of transparency, so how clear does it look, or how darker it sort of looks. So if I bring this way down and I move Australia a bit more across, we can start to see that there is some dots in Australia, sort of spread out in different locations. A few across in Perth in Western Australia, quite a few through New South Wales and Victoria, and a big chunk near Adelaide as well. There's also quite a few just off the coastline around. So it's a bit hard to see, but we have actually experienced some earthquakes definitely here. But you can see it's much smaller amounts compared to New Zealand and our other neighbouring countries. So the reason we're still having some earthquakes happening in Australia is that we've got a lot of pressure on our plate. We're in the middle of the plate and we're sort of protected, but there's all an earthquake needs to occur is for rocks to break under stress. And we're still going to have that stress by the other plates around us pushing on us as they're moving around and interacting. So this is a really cool way to be able to see the earthquakes in a much clearer way by having not even just a computer model, but having a 3D model makes it much easier to see these things. So now that we understand what an earthquake is and learned a bit more about how we monitor them, we're going to touch on probably the side you're maybe more familiar with, seeing the aftermath or the effects of an earthquake. So this is like the main impacts we'll observe. So the common ones is seeing either some damage to some roads or maybe some buildings, and even some things where it might move posts, like fence posts. And in this picture, we can see the entire railway line is completely been moved across from where it should be as that straight line. So it can cause a lot of problems to infrastructure, the things we build in our society. But we can actually see a bit more of a special type of effect in some cases. In some earthquakes, we can get an effect called liquefaction. And what's happening here is that the earthquake has occurred in a place where we have lots of sandy, wet soil. And that means that we can see in the picture what looks like a car has sunk directly into solid ground, which is a bit strange. So what I'm going to do now is I'm going to do a demonstration to help actually show how this kind of thing can occur. So I have got my very own tub of sandy soil, and we're going to treat this the same as that picture. So that picture was from an earthquake in Christchurch, New Zealand, back in 2011. So that that was about a magnitude 6.3. So pretty large earthquake, but also because it happened in the wet sandy soil, we saw this liquefaction effect. So I have got my tub of sand right here that's wet, ready to go. I am going to create a bit of a cityscape. So I'm going to place a building right here, and I'll also pop in a car over here. And we're going to see what happens when I create an artificial earthquake. So I am going to tap the container with this wooden block, and we're going to create some vibrations, and we're going to make some observations of what we see. It may or make a bit of noise, so sorry if it's a bit rattly. Let's keep an eye on it and let's go. Okay, we're starting to see some observations. Our building has fallen over and it's now actually sinking into the ground. And you may start to see there's a little bit of water starting to pool at the surface. So the water seems to be rising up through the sandy soil. Our car seems to be still upright, but the wheels are a little sunken in. But let's keep tapping and see what happens. Oh, that building is still definitely sinking in, but there's a little something here you may not see in the camera yet starting to pop up. Let's give it a little couple more taps. Oh, I can start to see yellow. Ah, so this little bit here was a bit of a surprise hidden in there. So that is a ping pong ball in my example. But what that represents is things underground that are a bit lighter or have a lower density. So that is things like pipes under the ground. Because the water is moving up, what happens is it allows heavy things to sink down and lighter things to move up to the surface. So while the building and a bit of the car has sunk into the ground, the ping pong ball or the pipes will rise up to the top. So you get to see quite a lot of strange things after the earthquake stops moving and the ground is now back to being more of a solid state. So pretty crazy to think about. All right, now that we've learned about some of the kind of more interesting impacts that sometimes can happen from earthquakes, we're going to talk a bit more about the innovations. What's the science, the engineering, and the technology used to help make earthquake science better? So, I've touched on a few things already a little bit. I'm going to do a deeper dive in. So, the first thing is around using that data that's collected. You already saw the 3D earthquake model that I showed you. And that's just one example of how we can actually interpret and better understand where earthquakes will be located and what countries or areas might be more likely to be affected. One of the other things we can do is make a risk model, and that is what the image on the right is with the rainbow sort of colors. Red represents a higher risk, and light blue represents a lower risk of earthquakes in Australia. So even though they're not as common here, we can see that there's certain areas more likely to have earthquakes. This is due to the rock types around it and also its previous experience of earthquakes. As we say, the rocks will break when earthquakes happen, and sometimes that happens at the surface, creating cracks or faults. When that happens, it means that earthquakes are more likely to still happen along those same areas. So we can often see more earthquakes happening in that same spot. And when we looked on the 3D model, we did notice that Perth, Adelaide, and bits of Victoria and New South Wales did experience more earthquakes on our 3D model. So they can be used as well together to help paint a picture. The other really important thing is that by understanding the risk of a certain region, first responders and people managing these hazards can better plan for what they expect to occur if we have larger earthquakes in these areas. And that's very important when it comes to managing a natural hazard. So, we're going to focus on an example that happened a couple years ago in Victoria in Rawson. So, it's very hard to see on this little map, but we wanted to point out where on the risk map Rawson is located and just showing that it's a bit further away from the main city centre of Melbourne. And we're going to dive into that example. So, this picture is from Melbourne in Chapel Street. And this is a building that was damaged from the earthquake that happened back in 2021 in Rawson. That was a magnitude 5.8. And so, even though Rawson, as an area where that earthquake originally started from, is about 170 kilometers away, the impact of that earthquake was felt very widely. So, felt down even down to Tasmania. Some people could feel that earthquake, all the way up to some people up in Brisbane and across to Adelaide. So, a very widespread felt earthquake. But in terms of damage, most of the buildings around in Victoria were not affected, but a couple were. And the reason being for this example here This is a much older building. So this was designed before we had regulations or clearer regulations around earthquake-safe buildings made of older bricks. And when bricks are shaken, a lot of the time, if it's high enough energy, they will break. And so you can see that though this building has lost a lot of its bricks, the buildings around it are perfectly fine and still standing. So, one of the important things that's come out of earthquake management and earthquake preparedness is making sure that buildings and roads and structures are able to handle an earthquake that matches or is near the highest range of risk for that area to ensure that human lives are safe during these events. So, that's really important. And each country will have their own rules around this. And for Australia, we don't experience as many earthquakes, but we still have to have a higher quality of buildings. And other countries like Japan, they need to have even more steps involved to make sure that they are even safer buildings. And we're going to look into that a bit now. So, in Japan, in some of their buildings, especially important buildings like a hospital, they will use a device called a base isolator system. And basically, it's this little device that goes underneath the building. So we're going to look at an experiment to see how this impacts. So we can see that device underneath the building that's kind of wiggling around is that base isolator. So what they did is they created a fake hospital building on top of some base isolators and put it on a giant shaker table to give it the same impact as if they had a big earthquake. And what you're watching is that building being swayed and moved by the base isolator. But inside the building, a few things are moving around, but it's not as destructive. In this example, you can already see the building falling apart, and this is without that same base isolation system. Things are getting knocked around and moved, and bits of the building are starting to break away. We can see that whole building is still standing, but we can see that it is causing a lot more movement than the first one. So even though both of those buildings use the same system, I think I would definitely prefer to be in that other one where we can see that base isolator right here is making a big difference for the safety of the people inside. And also it means afterwards that building isn't really badly damaged. So we don't have to then repair that building afterwards. There's lots of different types of base isolator systems. We can see this is just another version in a different building. But it's not just buildings we can be really clever with our engineering in. Another one we can do is this is a bridge in Los Angeles. And this was designed because the old bridge would continually get damaged during earthquakes. And what they've done is that they have created a series of lots of little pillars to hold up this bridge. And each pillar has something very similar to that base isolation system. And this time they call it a bearing. And basically, it allows that each individual pillar can move up to 76 centimeters. So a rule is about sitting here, so 76 is quite a lot if it needs to move that far when a severe earthquake is occurring. And this will allow motion of the bridge without it breaking apart and causing a lot of damage, which is very important. Probably an innovation you may not have heard of before is that it's not just about the direct buildings and things that are solid on the ground. We want to protect the things that are in motion or are in action on every day. So in Japan, they have a very special system set up that as soon as their seismometers will detect the beginnings of an earthquake, they have an automatic system that will send out a pulse of energy to shut down electricity to bullet trains. So that way they will automatically go into their emergency shutdown mode to safely stop. This means that the train is not in motion when the earthquake reaches them and means that it can be safely, people can be evacuated if needed, or they can safely stay in that train without it receiving any damage. So some really amazing things coming out of Japan because it is a country that experiences a lot of large earthquakes to make sure that the priority is safety for human lives, which is really important. And the last key innovation, which is probably something that we use every single day, is around communication. So almost everyone has at least a phone or an iPhone or has access to the internet, so we can get information as soon as we want or need it. And in fact, you're tuning in right today. And the important thing around hazards is the more quickly you can get information to the people who are in dangerous areas or about to be in dangerous areas is really important. So, having text messages, app notifications, and even just really rapid updates on websites for important live news is really important to make sure everyone's aware of what they need to do if they need to evacuate, or just being aware of certain parts of town may not be as safe to drive through if the roads are crumbly, or anything in between. And just being able to have access to news in a much more quicker way through TVs and phones and other apps is really important to get that information out. It is still very important to note that as much as technology has been an amazing friend to us through this process, if you're in an area that has experienced quite a severe earthquake, often more so in other countries, if the telecommunications or your phone lines or your internet lines go down, you may not have much access to some of that. Or if you're in a more remote or regional area, you may already not have as much access to that to begin with. So, older technology like radios or other communication systems that don't depend on the internet or telephone lines are still really important to use and help. All of it together just adds more options to ensure that everyone is informed as efficiently as possible. So, there's been lots that I've talked about today, lots about earthquakes and how we monitor them and all the things in between. But it's important to note that none of this work is done without a lot of help and support through lots of different people working together. So that's everything from the people detecting these things, like at the National Earthquake Alert Center, people who are doing the science. So whether it is the computer scientists working on data models, or even the people going out into the field to test these seismic stations to make sure it's working. And most importantly, the people that deal with the hazard as it's happening. So your first responders, your SES, and even those on the news front to communicate this information. All together as a whole network, we are able to better prepare, manage as it's happening, and manage afterwards earthquake hazards in our country and support our neighboring countries as well, which is really important. So if you found what I talked about today interesting, there's a couple different things you can do. You can take part in some of your own experiments. Maybe you want to test out making an earthquake safe building or bridge using some materials around your house or in your classroom. You could do your own liquefaction experiment with some wet sandy soil and try different objects to see how heavy or light or what happens to them. And the most important thing is to stay curious. If you are interested in what we've been talking about today, then one day you could be part of future innovations in the field of earthquake science. So I hope that you've learned a thing or two, and I'm ready to answer any questions in the Q&A that may have come up. So feel free to dive into that.
Excellent. Thank you so much, Tamara. And I never get sick of watching that liquefaction activity. I just think it's amazing. So we've got a few questions here from Tamara, who was asking a little bit more about that. So one was, how many earthquakes do you think there are per month?
Oh, that's a tricky one because we have earthquakes happening all the time. Very small earthquakes that we may not be able to feel as much, all the way up to really big events. So if we think about how many even just happen every day, there's quite a few happening around the world. So we're looking maybe over a whole year, we can have approximately 20,000 that could happen, and that's just maybe even just those smaller ones. So it could be up to 1,600 happening on a given month. But that's just an approximate. So lots are happening, way more that gets ever reported, and that's generally based off the USGS data that we have available. So yeah, great question. Lots more than you ever see on the news, definitely.
Absolutely. And we've got another one here. When was the last earthquake in Australia? Now, how about we say one that would have been felt by people?
Oh, even then, we can actually have in very localized areas, we can actually have quite a few happening on a given day. what I can actually do is I can bring up our live website that we use for earthquakes, and I can show you if any of them have happened actually today. So give me one moment. We'll bring across our earthquakes at GA. So you can access the 3D model and the one I'm showing you right now. And this is all freely available from our websites. And so what we can see here is the map of Australia. And what this represents is any circles represent earthquakes that have actually happened. And if it's red, it's happened in the last 4 hours. If it's orange, it's happened in the last 24 hours. And if it's yellow, it's a bit older. So sometimes a week up to 2 weeks. And so we can see that we've got several circles across Australia. There's a smaller one down here in Melbourne, one in the Northern Territory down in the middle of Australia. There's been several across Perth. And there's even one up here that's probably the biggest circle I can see. So if we click on this one, we can see that this happened today. This is in universal time. So just keep in mind, this isn't Australian Eastern Standard Time for what I'm using right now. And we see this was a magnitude 3.2. So we often get magnitude 2 to magnitude 3 earthquakes each day in Australia. And we can see already that just in the last couple of days, we've had several occurring. So people would have felt them if they're in those localized areas, but you wouldn't feel an earthquake that's a magnitude 3 in Perth necessarily all the way from, like, say, New South Wales or South Australia. That's a great question.
And Joe's just put the link in the chat for this, and we will share it in our follow-up resources as well. So you can actually explore this and, have a look over time for some of these earthquakes as well. So thank you for that question. And we also had another one here. Is how long does an earthquake usually last? Like, is there kind of, longer and shorter ones?
That's a great question. Yes, there definitely is longer and shorter ones. It depends on a few different things. It depends on the magnitude, so how big that earthquake was. Depends if it happened right close to the surface or whether it happened deeper in the earth. So like we saw in that 3D model, whether it was like that dark blue all the way down to red. If it's close to the surface, then you're more likely to feel it in that immediate area, maybe a little further out, which means that the amount of time will change depending on how close you are to the event. For example, there was a large earthquake in Japan back in 2011, and that was a magnitude 9, so quite a big version. And that lasted about 6 minutes approximately of shaking if you were in Japan at the time. So that's probably your extreme. On average, it might be anywhere from 10 seconds to maybe up to a minute for most of the ones we might experience in Australia.
Excellent, thank you. And Tamara was also wondering what other things could surface in an earthquake?
Oh, that's a good question. Basically anything underground that is lighter or has a lower density means the same thing than the sandy soil around it. So most commonly it will be pipes underground. Sometimes it can be wiring if it's in like a special case. That's mainly the human stuff. I'm not so sure about any other natural things that might come up. As long as it's lighter, theoretically it should be able to come up with it as well. But the most of the things we put underground would be probably pipes as the classic example. Yeah, great question.
Thank you. And for those of us that joined us for our dinosaur session this morning, they were talking about how some of the geography and the geology pushes the dinosaur bones to the surface. So if there was an earthquake in Winton with that really light sandy soil, that instead of it taking a long time for the dinosaur bones to come up with a shrinking and water, it could actually mean that some of those dinosaurs bones might raise slightly quicker. So you never know. But I don't know if they've got a lot of earthquakes there at the moment, but it could have certainly helped some of those bones come up. Okay, so this is a great one, and it might help some people doing the lunchtime trivia. What was the biggest earthquake in Australia?
Great question. Yes. So, biggest one in Australia that we've recorded was in Tennant Creek, which is in the Northern Territory. And that was a magnitude 6.8, and that was back in 1988. So again, a little while ago from now, but yeah, that's the largest we've experienced. So quite a large earthquake, but also being in a more remote part of Australia meant that it was less of an impact than if it had been the same type of magnitude directly in like a city centre. But yeah, great question.
Excellent. So hopefully everyone, if they're joining the trivia, remembers that one later. So
Yeah.
Dunoon Public School has this great question. What's the difference between a magnitude 3 and a magnitude 4 earthquake?
Great question. So how it works with the magnitude scale, it's basically just a maths equation to help represent the energy. And approximately as it jumps from a 3 to a 4 to a 5, each jump is approximately times by 30. So 30. So a lot of extra energy per each jump.
Excellent. And Ari was asking, if there's a volcanic eruption, will there be earthquakes in that general area too?
Great question. Yes, a lot of time earthquakes will sort of link up with other hazards. So if a volcanic eruption is occurring, that can cause shaking in the ground, which can be detected by the earthquake sensors. It just detects any shaking in the ground. Sometimes, in unfortunate situations, you can have a large earthquake, which may, if it's near a volcano, may cause it to erupt if it causes enough energy. So a lot of the time, earthquakes can trigger other hazards, or you can just get shaking in the ground from things like volcanoes or landslides, which also can be detected. So just because an earthquake detector doesn't mean it won't detect other vibrations that can still give the seismologist who are trained to look at it and go, I can see that's not an earthquake, but that still might be a problem. So yeah, very good question.
Excellent. And we've got the Sanson family asking, how does an earthquake form?
Oh, great question. Yeah, so earthquakes are just shaking the ground when the rocks are under stress. So this forms when you have pressures or stress created. So the most common way was with those plate tectonics. So for example, if you have two plates sliding past each other like this, you can get a lot of rocks breaking off and lots of tension and pressure as that's happening. And the same can happen as they're colliding. And you can get, in some cases, you can have plates where one will go underneath the other. And as it does that, lots of pressure and stress that can occasionally slip and rocks can break and release that energy. So most commonly, it's going to be triggered by those plate tectonic movements. But yeah, that's probably the most simplest way to think about it and covers the majority of those cases. Yeah.
Excellent. And that leads us into our next question is, do earthquakes form mountains?
Great question. In this case, no, not necessarily. What's happening there to form a mountain is when you have two plates collide, and instead of it going underneath, they collide and build up. And that happens when you have two kind of land or continent crust types. And what happens is they smush together, they don't want to go underneath each other, and they battle and build up, and we get this beautiful mountain forming. As that's happening, there will be some rocks a little bit breaking, so you'll get some earthquakes in that area. But mostly what's happening is it's bending and folding and sort of smushing together, for lack of a better scientific term. So you'll get a couple there during that process, but it won't be a big hub or cluster of earthquakes. You're much more likely to get it when they're either sort of like continually moving, so sliding past a little bit when they're pulling apart, but especially that going underneath because you've got constant rubbing and contact as it's going down.
Excellent. Thank you so much for that, your amazing knowledge, Tamara. That was the last of our questions just have come through. What a great overview of earthquakes, and really great that there's so many interactive activities linked to the Geoscience Australia website that students can actually follow up and continue to do. And that's a really great way for students to continue their learning and exploration as well. We will be sharing a whole lot of links as well, but thank you so much for sharing your knowledge on Earth Science Week and our fabulous programs that you have supported through Geoscience Australia today. So thanks very much everyone for joining us, and we'll see you soon at 12:30 for the Geology Rocks program. Thanks everyone.
Thanks, bye, and happy Earth Science Week, everyone.